All right, so previously we've been talking about this whole question of what happens when you have hidden variables. And the consequence of having hidden variables means that your estimator is not a single point on the, it's like space of probability distributions, but it's a set in some sense. Okay, so in order to do estimation, it's like in the presence of hidden variables, you can't just look at the closest point projection, if you will. It's like onto of a point onto a manifold of models, but you have to look at some sort of projection between manifolds in a sense. Okay, so we're going to study that now. So you can minimizing the divergence between a model manifold and a data manifold. Okay. So let me sort of first make a few remarks about what happens when your data manifold is just a point, right? So what happens is that the maximum likelihood estimator, right, is a minimizer of the KL divergence between an observed point Q bar to the model manifold in the fully observable setting. Okay, and then as we discussed before, what happens, it's like when you only have partial observations or when you have hidden variables, instead of having a single observed point, you have a data manifold associated with it, right? So in the hidden variable case, a single observed point is replaced with an observed data manifold. And if you recall, it's like the way you construct this observed data manifold is that you think of the observations, it's like with hidden variables, as only giving you information about the marginal distribution, all right? And then you sort of lift it, it's like to the full distribution by using Bayes' rule, okay? All right, so now, it's like the question of estimation can be cast in terms of trying to look at a minimizer of KL divergence, but instead of between a point and a data manifold, between a point and a model manifold, right? You want to find it's like minimizer of KL divergence between a model manifold and a data manifold. So that's what we'll do now. Okay, so the problem of estimation in the presence of hidden variables, right, can be viewed as sort of minimizing divergence between two submanifolds. Right, D, which is the data manifold, and M, which is the model manifold. Okay, so we can look at the divergence, the KL divergence between D and M. Right, so it's the minima of this integral Q bar Y, which is this marginal distribution, Q H conditioned on Y. Right, so this thing here is the joint probability distribution on the full space involving both the hidden variables and the observed variables, right? Whereas this is the estimate you had obtained from just having access to the observed variables. Okay, and then you have to right. And then you take the log of, again, Q bar Y, Y, Q, H conditioned on Y divided by P, Y, and H, and then C, dy, dH. Okay. So where the minimum between D and M, right, is taken with respect to QHY, so I have to vary over QHY and P, YH which is in the model manifold. So there appears to be a typo, it's like in the book, right? Because there it's like they are asking you to take a minimum over Q bar, but Q bar is sort of the observation, right? And then, so that's the observed point which comes from the data, and then what happens is that the data manifold is built around it as being the set of points, it's like of the set of joint probability distributions which are somehow compatible with this observation, right? And so this product here is the joint probability distribution on the full space, including both the observed variables and the hidden variables. Okay, and so since you don't know what this conditional probability is, you have to vary over all of them. And varying over all of them then gives you this data manifold, basically. Okay, anyhow. All right, so in any case, it's like there's this idea of taking the divergence, it's like between two manifolds, all right? You know, previously we had talked about how if you have a single point, it's like in a manifold, you can do either E or M projection, right, of that point onto a submanifold, right? But when you have two submanifolds and you're looking for the distance, then one way to achieve this, assuming the method converges, is to do this kind of alternating projection where you take a point on one set, you project it onto the second set, and then you take that point on the second set and project it back into the first set. And you know, it's like under sort of suitable assumptions, it's like, you know, it's like if you're sort of close enough, it's like to, you know, the minimizers, if you will, it's like then that kind of alternating projection algorithm will converge. right? So this is so to compute the sort of minimizer, right? We can use an alternating minimization algorithm. Right, if you recall, it's called the EM algorithm. Okay. All right, so let's state a few theorems about this. So the theorem is that the maximum likelihood estimator is the minimizer of the KL divergence from D to M. Okay. So let's try to prove this. Okay. So you can write down what this KL divergence is, right? So the KL divergence from a point in D, which I write down as Q bar Y. Right, this is the observed marginal distribution, if you will. Right. This is times Q H conditioned on Y, which is something in the data manifold, to P Y H, and then parametrically dependent on C in M, right, is given by d Q bar condition. So I'm just writing down this KL divergence, right? So this is the integral Q bar Y integral Q H conditioned on Y log Q H conditioned on Y dH. All right. So what I'm doing, right, is just using the fact that I'm taking the log of these, it's like products, right, and so this times this divided by this. So I can write down this log as log of this piece plus log of this piece minus log of this piece. So that's basically what I'm doing here. Right, so I'm just really expanding, it's like this term here, okay? All right, so that's one of the pieces, the log of just one of them, okay? Minus Q bar Y of Y integral Q H conditioned on Y log P Y H DH. Okay, so there's a dy. And of course, if you recall, there's one additional term, but the additional term is just a constant term, so that's a constant. Okay. All right. Right, so there are, if you will, that log term, it's like had 3 terms, right? And so there's 1 term, 2 terms, and then this third term is hidden in this constant c, okay, which does not depend on, so it does not depend on c or q h condition on y. All right. Yeah, so it basically depends on this q bar y term, right? So you know, it's like it's the same term for every point that's like in the data manifold, so it doesn't really matter. Okay, so you can just ignore it, because when you're trying to find this minimizer between d and m, it's like the relevant variables, if you will, it's like the relevant coordinates on m, right, correspond to c, right, which is a coordinate that's like on the data set manifold. And then the relevant parameterization of a point in D is on this conditional probability, right? Okay, because this term here is given to you, the only part which varies, it's like on D, is this conditional probability term. Okay, so that's why the fact that this third term, it's like doesn't depend on these two, means that, you know, it's like when you're trying to find a minimizer, it doesn't really enter into it. Okay, anyhow. So anyhow, so this is the KL divergence. It's like between these two things, right? And again, up to the term which doesn't, you know, it's like is an overall additive factor, if you will, to the KL divergence. So it doesn't affect the minimizer. So you can minimize this with respect to both of these two things. So we can minimize this with respect to both C and Q H condition in Y, right? Alternately by using the EM algorithm. Okay, and if you recall, it's like the reason why, part of the reason why it's called the EM algorithm is that essentially you do E projection and M projection and you keep alternating between the two, right? Which is the alternating use of E projection and M projection. So as a first instance, for example, you can assume that this conditional probability Q H dependent conditioned on Y is given, and then we minimize the KL divergence with respect to C. So let's call that star with respect to C. So let's see how you go about doing this. Okay, so you want to, so if this is fixed and then you want to minimize with respect to C, then you'll see that C only shows up, it's like in the second term, right? The first term, it's like doesn't have C anywhere. So you only have to minimize as like respect to this term. So we only need to minimize the second term in star with respect to C. And in particular, you actually only need to minimize the integral, right? Because this part here is again prescribed. Okay. So what I'm going to do is I'm going to take this integral term and I'm going to differentiate it with respect to C and then see what happens. So maybe let me try to keep that piece here. So let's leave that. All right. So I'm going to look at some term L, right, which is dependent on C and is conditioned on Q, right? So this is equal to the integral of QH conditioned on Y log of P YH C DH, right? So this is the part here. Yeah, this is the only part that's like which, sorry, yeah, this piece here, right? It's the only part that's like which varies as like respect to C, right, in this KL divergence. All right, so I can differentiate that and set that equal to 0. So dl dC is given by the integral. So I'm going to just integrate, differentiate under the integral sign, right? QH conditioned on Y, P that's equal to 0. So in order to minimize this, right, all right, sorry. So this is the condition we want to satisfy, right? And then the other thing you want to do is you want to minimize, again, this KL divergence, but now with respect to this conditional probability on Q, right? So to minimize, let's call it star, right? So to minimize star with respect to QH conditioned on Y, right? We use the following lemma. Okay, so I'm just going to leave the constant there. So the lemma is as follows, that the E projection from a point m to d does not alter the conditional probability distribution, q h conditioned on y, right, and hence the conditional expectation of h. Okay, so let's try to prove this lemma. Right, so if you're given now C, right, so now you want to project from M to D, so you're given a point on M, which is parameterized by C, right, and observe data Y, right, you want to find Q H condition on Y, right, that minimizes this scale divergence. Okay. So, so you have a constraint. That the integral of q h conditioned on y with respect to h is equal to 1, right? So this is a conditional probability distribution, but still a probability distribution on the hidden variables, right? So the minimizer is given by E projection. Of P Y H C, right, to D. And this involves solving for the following equation. So the integral of log q h conditioned on y divided by p h conditioned on y and cos c minus lambda delta q h conditioned on y dh equals to 0. And then lambda is a Lagrange multiplier which enforces this normalization constraint. Let's call that star star. Okay. And then So this implies that Q H conditioned on Y is equal to P H conditioned on Y. C. Okay. Which is the same as the conditional probability of H at this point, C. Right? Okay. So we're almost done. So that proves the lemma. Okay, so now let's go back and finish up the theorem. So if you substitute this equation into into this sort of condition, it's like for the projection, right, which is this integral of Q H conditioned on Y divided by P H conditioned on Y cos C, d cos C of P Y H cos C, dH equals to 0. Right, so we have this thing here, right? So we substitute this equality into this expression, that term becomes 1. So I just get that essentially, so this term becomes 1, right? So this gives me that the partial respect to cos C of the integral of P Y H cos C dH, right, is equal to d cos C, and then this, of course, is just the marginal distribution, right? So this is Py of Y cos C. So this is dd cos C of Py Y cos C is equal to 0, and then this is obviously the condition that you know, it's like this is the maximum likelihood estimator. So the maximum likelihood estimator is simply saying that you choose, it's like the point which is the maximum of the conditional probability as your estimator, right? And this is exactly what it is. That's the conditional probability. I'm setting the derivative to 0. That's going to be minima or maxima, right? So in this case, it's the maxima. And so that's so that shows what we set out to show. It's like, which is that the maximum likelihood estimator of the KL divergence. That the maximum likelihood estimator is a minimizer of the KL divergence from D to M. Okay. All right. And then it's like the next thing we'll talk about is sort of actually applying this EM algorithm. It's like in practice, right, for actually computing this maximum likelihood estimator. So let me just stop here for now.